As we continue to learn about digital logic, it's time to take a look at Boolean algebra and how it can be used to describe and to simplify our combinational circuits. Along the way, we're also going to learn about a new thing called Minterms. Actually, it's something you've been doing for quite some time, but I think you'll appreciate the simplicity of it. And we'll continue our focus on conversions between various things. For example, to go from Boolean to truth table to gate level representations. Suppose you have this circuit. F is equal to D naught C B A, or C A naught, or D naught A naught. This can be converted into a gate level representation with a single 4-input AND gate and then two 2-input AND gates. We need a converter for D naught and a converter for A naught. You'll notice that A naught is used in both of these AND gates. Let there be inputs D, C, B, and A. D naught, C, B, and A. We'll let that go to this AND gate. That takes care of that. We'll set up another AND gate. This time we need C. We'll take this term here. So there's our C. And we need A naught. So we'll put an inverter right here. One more AND gate. This time we need D naught, which comes from here. So there's D naught. And we need A naught. So this is D naught C B A. This is C A naught. And this is D naught A naught. And we OR them all together to determine F. One of the things you might be asked to do is solve this circuit for a particular set of inputs. For example, let D equal 0, C equal 1, B equal 1, and let A equal 1. We can write those values here as 0, 1, 1, and 1. We can translate them now to the inputs of this AND gate as 1, 1, 1, 1. That'll give us an output of 1. And we could stop there because we can see that F is going to equal 1 at this point. Because this is an OR gate, if any input is active, the output will be 1. But just for consistency, let's see what the other values are from these other AND gates. This becomes 1, and our A naught becomes 0, so that's a 0 there. This is a 0 and a 1, giving us a 0 there. But these two didn't matter. They didn't matter because we had a 1, and all it takes is one valid input to make this OR gate evaluate as true. We could have done that operation directly on our Boolean equation. F is equal to D naught, so that's 1, multiplied or ANDed with C, which is 1, ANDed with B, which is 1, ANDed with A, which is also 1, or C, which is 1, A naught, which is 0, or where are we at? So we're at D right now. So D naught is 1, and then we have A naught, which is 0. F is equal to 1 or 0 or 0, so F is equal to 1. You can see those results, such as this one right here, are identical to what we did in the gate level representations. While we're reviewing things, did you remember to construct your 3x5 converter? So your 3x5 note card converter. We need a column for binary, a column for decimal, and a column for hex. At this point in the class, we should almost make this a race. How fast can you fill this out? And the answer is it should take you only slightly longer than it takes me. So I'm going to do this in real time. Here we go. Remember, with hex, this becomes A and B. And now for the binary. So that's odd and even. Odd, excuse me, that's even, odd, odd. Now the pattern is 0, 0, 1, 1. Then the pattern is 4 zeros, 4 ones, and finally the eighths column. You're definitely going to want to have this note card converter when you do your exams and quizzes. It comes in extremely handy. Let's move on to our Boolean algebra properties. We'll start out with some of the simple ones. A or 1 will always equal 1. A and 0 will always equal 0. At the gate level, you could think of this as an OR gate, having an input of A and 1. Since we have a constant of 1 here, it doesn't matter what A is. The output will always be 1. For the second one, that's an AND gate with A and a hardwired constant of 0. If it's hardwired at 0, there are no conditions that A can take on that will make this evaluate as true. So the output will always be 0. A or A will always equal A. A and A will equal A. Or if you prefer, you could say the product of A and A is equal to A. At the gate level, the first one is an OR gate. It has 2 inputs. Those inputs are tied together with A going in to both inputs. The output will be A. And this is an AND gate with both inputs tied together. A goes in and A comes out. If you're interested, these properties do have names. This one is the null. This one is idempotent. If you're curious, that means same power. This is a fun one. A bar is equal to A. If we were to sketch that out on the gate level, that's one inverter. So if that's A coming in, this is A bar. And if we run it through another inverter, we end up with A bar. And that's involution. 0 or A is equal to A. 1 and A is equal to A. Here's the OR gate. We have inputs 0 and A. So 0 will never be active, which means that the output will just be A. And here we have an AND gate with inputs 1 and A. Since 1 is always active, all we have to do is look at what A is doing. This is called identity. A plus A naught is equal to 1, and A and A naught is equal to 0. Using our inversion bubbles, that looks like this. Here's an OR gate with input A, and we put an inversion bubble right there. So this OR gate has A or A naught. And no matter what happens, this will always be a 1. For the second one, it's an AND gate. There's the inversion bubble. So this takes in A. And you can see there's never a condition where the truth table will be met, right? You'll never have a condition where the input here and the input here, which is to say on the right side of that inversion bubble, will be equal to 1. Therefore, the output will always be 0. This is called the complement. The next property is called De Morgan's law. And it goes like this. B or A naught is equal to B naught A naught. If we were to sketch this at the gate level, this is an OR gate. Actually, it's not an OR gate, it's a NOR gate with inputs B and A. And De Morgan's law tells us that that is equal to an AND gate with B naught and A naught as inputs. We could look at this another way by saying that B and A naught is equal to B naught or A naught. On this side, we have a NAND gate with inputs B and A. And on this side, we have an OR gate with inputs B naught and A naught. This first one tells us that a NOR gate is the same as an AND gate, provided you invert the inputs. The second one tells us that a NAND gate is the same as an OR gate, provided you once again invert the inputs. If you wanted, you could show that as a truth table. For example, for this one here, inputs B, A, output F. So it's an AND gate. So we're looking for a condition here where we have A and B, and then we invert that. So that would give us 1, 1, 1, 0. And now for this one, the truth table, we're looking for a condition where at this side of the inversion bubble, we have a 1. And it looks like that would occur here, 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 and here. So you can see that the truth tables for these are indeed the same. By the way, I should backtrack a little bit to our previous lecture. You'll recall that we talked about the distributive rule. And in that rule, we said that A ANDed with C or B could be handled like you would a mathematics problem, where you would FOIL this, giving you CA or BA. But there's another part of the distributive rule that I didn't talk about, and that is A or CB is equal to, quite surprisingly, CA ANDed with BA. Your textbook author called this one tricky. Tricky because it doesn't follow the normal algebra rules that we all know. This was straightforward. You knew what to do with that one. But this one, not so much, because there's no rule that says you can go from A and cross over like so. So you're just going to have to put this one on your note card and be on the lookout for it. Now that we've reviewed all of these rules for Boolean algebra, let's work a bunch of examples to see if we can make some sense of this. Let f equal to c b naught or cb or dA. Now, we could certainly build this circuit as is. We would need 3 dual input AND gates and 1 3-input OR gate. But it could be simplified. We could rewrite this as C over B naught or B. You'll notice there's a C in each of these terms, so we're just using the associative property. Or dA. This term B naught or B, that's this one here, we'll always evaluate as true. As far as the equation goes, it becomes C and 1 or dA, or simply f is equal to C or dA. This circuit and this circuit are functionally equivalent. They provide, or they boil down to the same truth table. I would argue that this one is considerably easier to construct, though. Here, we would need a 2-input AND gate and a single 2-input OR gate. For a bit more practice, and just so we understand, let's take this equation and convert it to a truth table. For convenience, we'll start by writing the equation here. That's input D, C, B, A. Intermediate wires C, B naught, CB, and DA. And finally output F. 0, 1, 0, 1. For the intermediate wire C, B naught, we're looking for places where C is true, but B is not true. So that'd be here and here. So we can go ahead and mark those in. That would be 1, 1, 0, 0, 1, 1, 0, 0. All other places would be 0. For intermediate wire CB, we're looking for conditions where C is true and B is true. So that would be 0, 0, 1, 1 and 0, 0, 1, 1. It would be 0 for all others. And finally, for intermediate wire DA, we're looking for conditions where D is true and A is true. So that'd be 0, 1, 0, 1, 0, 1, 0, 1, 0 for all others. And now for F, we look across these rows, and we're looking for a value of 1 in any of the 3 intermediate wires. Finding none, these are all zeros. Here we have 1s and 1s, so this becomes 1, 1, 1, 1. Here we have a 1 there, 0, 1, 0, 1, and finally 1, 1, 1, 1. If we were to slide back here and look at our simplified answer, let's see if this makes any sense. So if f is equal to C or dA, let's write that here. F is equal to C or dA. When we look at the truth table for F, we see this and this. If we look over to our inputs, that's just C. So if C, period, right? If C is active, F will be true. As for D and A, let's get a different color here. Well, here's D, and then A. So that'd be this one, this one, this one, and this one. So that accounts for these two here. This is DA. This is DA. DA again. And finally here as DA. So it looks reasonable. Our truth table follows our Boolean algebra. Let's try something a little more tricky. Let f equal to C naught, B naught, A, or C naught, B naught, A, or C naught, B, A, or C naught, B, A naught, or C, B naught, A, or C, B, A. Now this one has a lot of terms, and it gets a little bit tricky because you have to find the patterns. For this particular one, we could argue that these two terms are linked by a C naught, A naught. These terms are linked by a B naught, A, and these two are linked by a B, A. If we rewrite this, f is equal to C naught, A naught by B naught or B, or B naught A by C naught or C, or B A by C naught or C. If we simplify the circuit, f is equal to C naught, A naught, because this piece here always evaluates as 1. So C naught, A naught, or B naught, A, or B, A. Now you'll notice that there's an A in both of these terms. So that becomes f is equal to C naught, A, or A by B naught or B, which can be rewritten as C, A, or A, or if you prefer, A or C naught A. At this point, we look back and we remember that tricky problem that the author described, where we can use the distributive property to solve this. So we would say that f is equal to C naught or A ANDed with A naught or A. So finally, we can just say that f is equal to C naught or A. Once again, this is that pesky distributive property. Remember, there's two of them. We have one that says A ANDed with C or B yields CA or BA, where you essentially FOIL. The other property, the tricky property that your author spoke about, says that A or CB is equal to C or A ANDed with B or A. And it's this distributive property that we used up here. All right, maybe it's just me, but I find these operations a bit tedious. It is so easy to make a mistake with your pen. You'll be glad to know that there are better ways to handle this. For example, let's review this Boolean algebra. If we were to do a truth table, C naught, B naught, A naught would be as 0, 0, 0. This would be 0, 0, 1. This would be 0, 1, 1. 0, 1, 0. 1, 0, 1. And 1, 1, 1. If you have your handy-dandy 3x5 note card, you could look at this and you could say, this is the 0 decimal. 1, 3, 2, 5, and 7. So now when we go and build that truth table, C, B, A, output F, we can talk about this being the 0 term, the 1 term, 2, 3, 4, 5, 6, and the 7th term of the table. Looking at your note card, you can see, for instance, that this number here is binary 3, and we've just written it as the decimal form. Going back to our original equation, we know the circuit was sensitive to 0, 0, 0. So we can put a 1 here for that particular term. We knew it was sensitive for 0, 0, 0. So we can put a 1 here. And there was a 2, a 3, a 5, and a 7. So this particular circuit was sensitive to terms 0, 1, 2, 3, 5, and 7. So rather than describing all of this, we could put it into a much more compact term and simply say F is equal to the summation of what are called minterms. And then it's the 0th term, the 1st, 2nd, 3rd, 5th, and 7th. We call this designation compact minterms. So this is the compact sum of minterms. Going back to our original equation, we would describe each of these as minterms. Minterms meaning that in a 3-input system, each of the 3 inputs is contained within each term. So this particular one has input C, B, and A. So every single one of these minterms identifies all 3 inputs. Okay, so that is our definition of minterms. This is not a minterm. It's certainly the same circuit, right? This here, if we were to expand that out, would equate to this truth table, but we are not using minterms in this description because we don't contain each and every term. This is not a minterm, and this is not a minterm because they do not contain all 3 of the inputs. On a related note, there's a very important point we need to make about this truth table. The truth table is the truth table. Okay, there's no question about that. Given these inputs, C, B, and A, the output F will be as you see it here. However, there are many ways or many different circuits that could be built to give you the same truth table. For example, we could have used this circuit. We could have built that circuit to make the truth table. We could have built this circuit, and it would have had the identical truth table. This circuit would have had an identical truth table. This circuit would have had an identical truth table. So all of these, as different as they are, all produce the same truth table. There is a fancy word to describe this, and that is canonical, known as one form. So we come over here. We could say that many unique equations can describe a circuit. Canonical. One form. We can talk about a truth table. For example, a 3-input truth table. That table could be built using many different circuits. We could have a circuit built entirely out of NAND gates. We could have a circuit built with an array. You could even have a circuit built completely using NOR gates. Whatever you would like. The important piece is that many different circuits could be built to produce this single truth table. Before we move on, let's make sure everybody's tracking with regards to these minterms. So if I had this equation, d c naught b a, or c b a, or d naught c b a. If I were to ask you to identify the minterms, could you do that? The first thing we need to do is recognize that this is a 4-input system. We have inputs D, C, B, and A. So 4 input. Then we need to look at each of our terms and see if they contain all 4 inputs. This one does, this one does, this one does not. So these are not minterms. We could expand this. This becomes D, C, B, A, and this D naught, C, B, A. Now we have the correct circuit. This is much better because now we have all the minterms. In fact, we can modify the circuit to use the compact sum of minterms if we like. This becomes 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, and 0, 1, 0, 1. If you have your note card converter handy, 1, 0, 1, 1 is a D in hex. 1, 1, 1, 1 is an F. 0, 1, 1, 1 is a 7. And 0, 1, 0, 1 is a 5. So the compact sum of minterms would be 5, 7, D, and F. Or I suppose you could also wrote it as F is equal to the minterms of 5, 7, D is 13, and F is 15. Let's end this discussion with one great big ugly example. So we're going to start with a compact sum of minterms. We're going to jump to a Boolean simplified. We'll show how to go to a truth table. And finally, we'll show different gate level representations of a circuit. Keeping in mind that there can be many different gate level representations for the same circuit. But there can only be one truth table. For this example, let F equal the compact sum of minterms for 0, 1, 2, 4, 8, A, and F. We'll start with the truth table. Input D, C, B, A. We'll let this be a decimal form, and then we'll let this be F. Actually, let this be hex instead. I think that might be a little more descriptive because our compact sum of minterms was expressed in hex. And now, as far as F is concerned, we know that when we have these compact sum of minterms, that F will evaluate true for every number in this list. So 1, 1, 1, 0 because there is no 3 here. There is a 4, no 5, no 6, no 7. There is an 8. There is an A, and then there is an F. So that is the truth table for our equation. As for the Boolean equation, F D naught, C naught, B naught, A naught, which is minterm 0, or D naught, C naught, B naught, A, which is minterm 1. So that's a 2, 4, 8, 10, and 15. To simplify this with Boolean algebra, we need to look for patterns. And it's not always clear at the beginning which patterns we should look for. So as a demonstration, I'm going to start out with even and odd. So we'll start out with the even terms. Here's 0, if 0 can be even, but 2 certainly is. 4, 8, and then we'll put the other terms down here. Looking inside the brackets, these two appear to have D naught, C naught, so we could combine those. And these two have a D, C naught. So F is equal to A naught, put a bracket here, D naught, C naught, B or B naught, so that's this and this, or, let's see, D, C naught, B naught or B, which takes care of this one and this one, and then we'll just bring all the other terms down. We rewrite this, D naught, C naught, plus D, C naught. Hopefully I haven't made any mistakes in here as I transpose these. Looking inside, looks like we have a C naught for each of these. Our last step is to distribute this A naught. So that becomes C naught, A naught, or D naught, C, B naught, A naught, and then those other terms that we've carried along. Let's fix a mistake here. This would have been B naught from here. This would have been B naught and B naught. Sorry about that. Anyway, we can rewrite this as C naught, A naught plus D naught, B naught ANDed with C, A naught or C naught A ANDed with D, C, B, A. You may recognize this as an exclusive OR. At the gate level, this is our circuit. We start with that exclusive OR with inputs C and A. That goes to an AND gate along with inputs D and B. Actually, it's D naught, B naught. We have an AND gate with C naught, A naught. And we have a 4-input AND gate with inputs D, C, B, and A. And all of that is ORed together. Now that's not an unreasonable circuit, but maybe we can do better. Remember that our initial split was even and odd. So what we did is we just took all the even minterms and put them in one spot and all the odd terms in another. Let's try this again, making a different set of assumptions. This time, let's try collecting terms with D naught, B naught, and then we'll collect terms with C naught and A naught. F is equal to D naught, B naught with C naught, A naught, or C naught A, or C A naught. Next, we collect all of our terms with C naught, A naught. And then we have this outlier, term number 15. You'll notice that this min term right here appears in both of our collections. Now we can do some simplification. That first one is a distributive property, collecting things with C naught in them. Then we collected things with A naught in them. You'll notice that this term appears twice. Here it is as C naught A naught, and again as C naught A naught. Some simplification of this part now. When we do that, all of these pieces go to 1. When we do that, you'll notice that this is D and D naught, so that term becomes 1. So this entire thing inside here becomes 1, leaving us with C naught A naught. So our final equation is D naught, C naught, B naught, which is that piece there, or D naught, B naught, A naught, which is this piece here, or C naught, A naught, or D, C, B, A. We can sketch that circuit on a gate level very quickly. A 2-input AND gate for C naught, A naught. Here's a 3-input AND gate for D, C, and B. So D naught, C naught, B naught takes care of that and that. Here's another 3-input AND gate. This time with D naught, B naught, A naught. And finally a 4-input AND gate with D, C, B, A. As we said multiple times already, remember that there are many different circuits to make the same truth table. You would find that this circuit is every bit as viable as this circuit. And while we're at it, we may as well show the array just for the sake of being complete. Input D. As I recall, there were 7 minterms. There was minterm 0, 1, 2, 4, 8, A, and F. Minterm 0 is programmed using D naught, C naught, B naught, and A naught. On the other end, minterm F is D, C, B, and A. I'll do one more example, then leave it to you to do the rest. Minterm 4 is composed of 0, 1, 0, and 0. We really should be putting dots here to show where the lines connect. So minterm 0 is 0, 0, 0. Minterm 4 is 0, 1, 0, 0. Minterm F is 1, 1, 1, 1. As a side note, this array style is rather clumsy to draw out by hand. However, when you get into the simulators, it makes it so much easier, especially when you have the ability to click on a wire and it lights up. For example, in a simulator, you could come over here and you could click on the D not line, and every single connection, every wire that's connected to that will light up very bright. So it's actually quite quick to troubleshoot. All right, we started out somewhere talking about an expression using a compact sum of minterms. We described a truth table. We did some Boolean algebra and arrived at this circuit. We did the Boolean algebra again and arrived at this circuit. And then, just because we could, we used an array style. One of the questions that we need to answer in the near future is which one of these circuits is the best? And is there a way to find a simplified circuit faster? And it turns out there is. There's a tool called the Karnaugh map. For this particular circuit, it would have looked something like this. By the way, I'm just going to show you that this exists. I'm not going to explain why, at least not yet. That will be an upcoming lecture. D, C, B, A, where DC takes on value 0, 0, 0, 1, 1, 1, 1, 0, and BA will take on values 0, 0, 0, 1, 1, 1, or 1, 0. I'll now write the minterms into each square. So 0, 0, 0, 0 is minterm 0, and 1, 1, 1, 1 is minterm F. And now we'll write the rest in. So 0, 1, 2, 3, 4, 5, 6, 7. Really peculiar. This is 8, 9, A, B, C, D, E, and F. As I recall, our minterms were 0, 1, 2, 4, 8, A, and F. So everything else was a 0. Now the beauty of this Karnaugh map is we need to look for terms that are adjacent to each other. So this particular one is really interesting because it has flying corners, which occurs when we have C naught, A naught. So here's C naught right there, and here's A naught. So C naught, A naught describes the corners. Now this is a peculiar one. This is all out by itself. So that's D, C, B, A. And then we'll find out that these here are adjacent. So using the Karnaugh map, we would simplify the circuit as C naught, A naught, plus D naught, B naught, A naught, or D naught, C naught, B naught, or D, C, B, A. And I think you'll agree that this is a much, much more elegant way of describing circuits than all of this Boolean algebra stuff we did over here. Anyway, I thought you might appreciate that, knowing that there are other tools that we can use to simplify our circuits.